Okay, so in this video, we will be discussing about the DFS for graph data structure. So DFS, as you know, it stands for depth first search. I will try to explain you DFS based on the example that is seen on your screen. All right, so this is a graph. Okay, so this is a graph that can be described as a set of vertices V, which include 0, 1, 2, and 3. Okay, and a set of edges. Okay, so these are bidirectional edges. So if you have like an edge from 0 to 1, so you also consider an edge from 1 to 0. That is like if you can travel from 0 to 1, you can also travel from 1 to 0 back. Okay, so that you need to keep in mind regarding the bidirectional edges. All right, so this edge, the set of edges would be represented something like you have 0, 1, then you have 1, 0, then you have 0, 2, then you have 2, 0, and 2, 0, and then you have 1, 2, then you have 2 and 1, then you have 0, 3, and you have 3, 0. Okay, so this is how you represent a graph, and the graph would be equal to G, set of vertices, and E. Just substitute these values and you'll get the definition of the graph. Okay, so I won't be I don't want to like waste time in explaining what exactly is the terminologies of graph and all. What we'll do is we'll directly come to the point, and how does the DFS process each of the node. Okay, suppose we invoke a DFS function on the node 0. Okay, so our DFS guy, he's over here. Okay, suppose that this is the guy who needs to go to all the different nodes in this graph, and we start our journey from the node 0. Okay, and here the graph, one thing that we need to keep in mind in graph is that we need to also track where all we are visiting. Okay, so if we are visiting any of the nodes, we need to have an information that we have already visited a particular node. Suppose you visit a node 1, so here just need to remember. Okay, so you just need to remember that we have already visited this node. Otherwise, what would happen is if you start your journey from 0, you feel that okay, you should be going to the node 2, so you go to 2. Okay, and you're not storing. So remember that you are not storing the information about visiting that particular node or not. Okay, so from 0 you go to 2, and from 2 you go to 1, and from 1 you go to 0, and 0 again sees that okay, so 2 is not visited. Okay, so it goes again back to 2, and then here, so this would be like an infinite loop that will keep on continuing until and unless we have a means to know that we have already visited these particular nodes. Okay, so for that particular thing, we need to keep an information about something called the visited array. Okay, so visited array. So visited array is nothing but you just have an array whose size is equal to the number of nodes in the graph. Okay, so here each box is allocated for a given node in the graph. That is, you have one box for 0, one box for 1, 2, and 3. Okay, on each of these boxes would contain true or false whether that particular node is visited or not. Okay, so if you start your journey on the node 0, we'll mark node 0 to be visited. Okay, and rest of all of these would be false by default. Okay, so it will be false. That is, these the node 1, node 2, and node 3, these are not visited. Okay, so from 0, if you decide okay, you want to go to node 2, so you just move to node 2 and you just mark node 2 to be visited. So here I'll just mark it to be true. Okay, so I'll just mark it to be true. So 0 is also true, and 1 and 3 would be false as of now. Okay, so these two would be false as of now. Now from 2, we see that okay, there is a node 1 that is not yet visited, and like how do we get to know that it is not visited? We just simply see that okay, so node 1, we just every time we query the visited array to know a status about a node. Okay, whether the node 1 is visited or not already. So here we just query the visited array. So we just query visited of 1. Okay, and it returns as false. That means the node 1 is not visited, and we can go to node 1. So we move to node 1 and we mark visited of 1 to be true. Okay, so here it was false before. So what we do is we mark this this false to be true. Okay, so now node 0 is done, node 2 is done, and node 1 is done. All these are true. And we have made a jump over here. So this is visited, this is visited, and this is also visited. Now coming to 1, we see that where are the possibilities that we can move from 1. So we can move to 0 and we can move to 2. So here we see that both 0 and 2 are visited, and hence we do not need to go anywhere else. So we just simply return back from where our functions was invoked. So DFS of 0 would have given rise to DFS of 2. So DFS of 0 is like the place where DFS of 2 was born, right? So it simply goes back to the place where it was born. So DFS of 1 was given rise by DFS of 2. So it will simply go back to the place it was born, the function call was born, and it will reach till 0. Now DFS of when we are back to 0, we see that we have another node that is not yet visited and it is connected to 0. So we simply go to the node 3 and we mark it as visited. Okay, so it was false. So we need to traverse to that particular node. Okay, so we just simply query visited of 3. If it is false, we just simply visit that particular node. Alright, so from 0 we jump to 3 and we mark it as visited over here, and from 3 we see that are there any other nodes to be visited, and here we see that there is none to be visited. So we simply go back to the parent, we go back to the place where DFS of 3 was called. Okay, and that is this particular 0, and here there are no more nodes that are adjacent to 0 that needs to be visited, and here we conclude our entire traversing of the graph. Okay, so here also you see that here all the entries have become true. Okay, so there might be case when some of the entries might be false, and that is the case when you have disconnected components also in the graph, and we will come to this particular concept later on. Okay, so disconnected components in a very simple language means you have like two graph components which are not connected by edge. So here you see that these two are totally different from each other. So there is by no means you can travel from one of these nodes to node in this particular graph, because there is no edge as such that connects these two components together, and this is known as disconnected components, and we'll come to this particular concept later on. Alright, so DFS is simply like, in a very nutshell, so you go to a node, you mark that node to be visited. Let me write it down so that it's more clear to you. I'll erase this off. Okay, right. Okay, so what we do is, first point is we visit a node, okay, and mark it as visited of current node. We mark it to be true. Okay, that's the first thing that you do when you're visiting a node. Okay, and the next thing what you do is we traverse all the neighbors for neighbor in graph of the current node. Okay, the graph of current node will give you all the neighbors of that particular current node, and we just see if all those nodes, we just see whether these nodes that are adjacent to that particular node, the current node, are visited or not. If at all it's visited, if it is already visited, okay, so we simply ignore. Okay, we simply ignore. That is like continue in C++. And else, if it is not visited, okay, if that particular node is not visited, what we do is we simply give a call to DFS of that neighbor. Okay, so that it spawns a DFS function for this particular node, the neighbor node basically. Okay, so 0, that's what I was telling you, right? The function which gives rise to another function call, that is DFS of 0, would be giving rise to DFS of 2. Okay, DFS of 0 would also be giving rise to DFS of 3 later on. So DFS of 2 knows where to go back when all the nodes that are adjacent to 2 are visited. Okay, and similarly DFS of 2 here, DFS of 2 had given rise to DFS of 1. Okay, that's the place where we get to know that once all the adjacent nodes to 1 are visited, where do we need to go back? We need to go back to 2, since it was the place which gave rise to DFS of 1. Alright, so let me go to the Visual Studio Code so that we can implement this particular function over here. Okay, the very first thing I'm going to do is I am going to declare a graph. Okay, so declare a graph first. Graph with how many nodes? We have 4 nodes, right? Okay, so just see this particular thing. So we have 1, 2, 3 and 4. Okay, so 4 nodes are there. So I'll just say vector int graph of 4. Okay, so this is how you declare a graph. So if you haven't seen my adjacency list representation of graph in C++ video, you can just go ahead and see that. All right, so here what we do is we declare the variable for a graph, for storing a graph, and now we need to make a function that can add edge to the graph. Okay, so add edge function, we'll just write it down something like this: void add edge. Okay, and I'll accept the graph as the first parameter, so I'll have graph. And what else do I need? I need like which are the edge, which are the nodes between which I need to establish an edge. So I'll say int source and int destination. Okay, and since this is a bidirectional graph, so since this is a bidirectional or undirected graph, I would say undirected graph, I need to have two sentences, two statements basically. That is like graph of source dot pushback destination. Okay, and similarly we need to have another statement that is graph of destination dot pushback source. Okay, so it will add the edge to the graph. All right, so in the main function, let's add the edges to the graph. Okay, so what I'll do is add edge function, add edge. First parameter is the graph itself, and between what all nodes do we have the edges? Okay, so let me colorify this. So we have this as 0, then this as 1. Okay, this is not a good color, so I will have 0. Let me erase it first, a circular erase. All right, so this is node 0, this is node 1, this is node 2, and this is node 3. Okay, so now we have an edge between 0 and 1, so I will just add an edge between 0 and 1. Okay, then we have an edge between 0 and 2. Okay, so I'm taking into account this particular edge, so this we have done. And then we have an edge between 1 and 2, so I'll just add an edge between 1 and 2, add edge graph of 1 and 2. Then we have an edge between 0 and 3, add edge graph 0 and 3. Okay, so let me make sure that we have added all the edges. So we have the edge between 0 and 1. Okay, so this particular edge is 0 and 1, so this one is done. Then we have an edge between 0 and 2, so 0 and 2, this one is also done. Then we have an edge between 1 and 2, so 1 and 2, this one is also done. And then we have an edge between 0 and 3, so this is also done. Okay, so now by this time, like the moment these 4 sentences are executed, we have the graph constructed. All right, so now what we need to do is, as I told you, now we need to have something called as visited array that we talked about here. Okay, so we need to have this particular array, and this is the size of the number of nodes. That is, here we have 4 nodes, right? This is 1, 2, 3 and 4. So this visited array should be containing 4 elements, that is 0, 1, 2 and 3. Okay, so 0, 1, 2 and 3, right? So here let's declare that first. So vector bool. Okay, so vector bool of visited. Okay, and its size would be how much? Its size would be 4. Okay, instead of like typing 4 again and again, let me declare a variable called constant int total number of vertices, and I will use this v everywhere. Okay, so visited of 4, and initially none of the nodes are visited, so I'll mark all of these values to be false. Okay, so this is how you declare a vector and also initialize the default values. Okay, so this would declare a vector of boolean values, and the size of the vector is v, that is like size would be 4 since we have declared v to be equal to 4 here, and the initial values and the values of all the elements inside this visited vector would be false initially. That means it simply indicates that none of these nodes are visited here. Okay, so after that particular statement, we'll have a visited array, and all these values would be false. Okay, इसका नाम है visited. Okay, and now we need to declare something called as DFS, and we need to pass the graph, we need to pass the visited array and the current node where we have started the DFS function. Okay, so let's name it as start node. Okay, so int start node. Okay, let me give an example of 0 only, like we are starting our DFS journey from the node 0. Okay, suppose that we are starting the journey from 0, and which are the nodes that it visits and in what order will determine from here only. Okay, so in start node is 0, visited we are passing, graph is also we are passing, but we do not have this DFS function defined for us. Okay, so our task now is DFS, our task now is defining this DFS function. Okay, so let's have void DFS, and the very first parameter is the graph itself. So I will accept the graph as vector int graph. Okay, so I accepted the graph. The next parameter is visited boolean visited vector. So this would be a vector bool of ampersand visited. So why I'm taking ampersand is because I want to pass this visited boolean vector via reference. Because if I'm invoking another call to DFS inside the body, I need to pass the same visited vector rather than passing a copy of it. Okay, so for that reason I am doing this ampersand visited, and I need to keep a track of the current node. Okay, so for which node is this DFS function working for? Okay, so so when you are on the node 0, right? So when you are on node 0, so it will be working something like DFS of 0 current node, this current node value. So this current node would be having 0 when you are invoking DFS of 0. Now DFS of 0 would invoke DFS of 2, so current node value would be 2. Okay, so current node simply indicates that this entire body needs to be executed for that current node. Alright, so what do we do? So as we discussed here, so what do we do? The very first thing that we need to do is we need to mark visited of current node to be equal to true. Okay, so this is the first step. So let's do that. And before that, let me print. Okay, so let me print the current node, like which is the node that we are processing right now. So I'll say processing node and current node. All right, and I will mark this current node to be visited. Okay, so I'll just simply invoke visited of current node is equal to true. Okay, so visited of current node is equal to true. So simply we do the statement. So we mark the current node to be visited. Okay, so that we do not so that we do not process the same node again. And for that we are just keeping track of the visited visited vector. All right, and next what do we do is so the first step we have taken care of. Next what we need to do is we need to see for all the neighbors of the current node. For all the neighbors of current node, we need to see whether we have visited those nodes or not. Okay, for example here, if you see 0, so here we just see that for all the neighbors of 0, means 1, 2 and 3. So 1, 2 and 3 are the neighbors of 0. For all the neighbors of 0, we need to see which are the nodes that we have visited. So here we have not visited anyone. So here what we do is, if it is not visited, we simply invoke the DFS of that particular node. That means we are visiting that node and we want to carry on forward like that. Okay, so simply here what we need to do is for int neighbors in graph of current node. Okay, so graph of current node. So here you see that graph of current node would be containing the neighbors of the current node. Okay, so if you do not understand like how is graph of current node containing the neighbors of the current node, you need to like revisit like how adjacency lists are stored, and it will make it clear for you. Okay, so like just to give you a quick highlight on how it is stored. So adjacency list of this entire graph would look something like this. So we have 0, and it will be storing all the neighbors of 0. So you have 0, that is 1, 2 and 3 would be stored in the adjacency. The neighbor, that is graph of 0 would give you basically this list. These are the neighbors of 0. The graph of 1 would give you what? So 1 ke neighbor kaun hai? So we have 0 and 2. So this 0 and 2 would be stored in the neighbor list of 1. Then 2 ka kya hai? 2 ka hai 0 and 1. So it will be having 0 and 1. 3 ka kya hai? 3 ka will be only containing 0. Okay, so this is how the adjacency list would be stored. Okay, let me erase the entire thing again. All right, so now what we do is for every neighbor, we just see whether it is visited or not. If it is visited, if visited of neighbor, wait, here it will be neighbor. Okay, so let's keep the meanings correct. So if neighbor, if visited of neighbor, okay, so this particular if statement, it will simply check if the neighbor is visited. Okay, if the neighbor is visited, what do we need to do? We don't need to do anything. We don't need to visit that particular node, right? So if the neighbor is visited, we simply do continue. That is, ignore visiting that node, because if we visit, it will become an infinite loop, right? Again and again we keep on visiting. That's the reason why we are keeping track of the visited nodes, right? Okay, so if visited of neighbor is true, we simply continue. Otherwise if the neighbor is not visited, okay, so then only it will come to the else statement. We need to invoke the DFS function by passing in the same graph, passing in the visited boolean array, and instead of the like the current node, we need to pass in the neighbor. That is, invoke the DFS function for that particular neighbor. All right, so if you just closely observe, this entire thing, this entire if else thing can be condensed into simply checking not visited wala thing. That is, I'll simply write if not visited of neighbor, I would simply do DFS of neighbor. Okay, simply this. If you just do, that is more than enough. So if neighbor is not visited, we invoke the DFS for the neighbor. Otherwise, if it's visited, it is automatically ignored because we do not have an else statement here. All right, so this is pretty much it. That's it. The DFS function is this itself. And let us just try. What do you say? Try compiling this particular program and see what output do we get. All right, so we'll say g++ dfs.cpp, and I'll say a.exe. All right, so here it says processing node 0, 1, 2 and 3. Okay, let's track it down. So here it is like processing node 0 first. Okay, so processing node 0. Okay, so now it sees that after 0, where is it going? So after 0 it is going to 1. Okay, after 0 it is going to 1. Okay, after 1 it needs to go to 2. Okay, after 1 it is going to 2, and then it is coming back to 1, coming back to 0, and then it needs to visit 3. Okay, if you want to track the coming back also, like what do we do is we'll simply say that, so let's at the end put that cout there are no more adjacent neighbors unprocessed. There are no more adjacent unprocessed neighbors to current node. Okay, let's include this particular line into our code. So the control will come over here when it has done with the processing of all the neighbors of the current node. Okay, and then we are simply printing there are no more adjacent unprocessed neighbors to the current node. Okay, let us compile this particular program and see like what output do we get. So g++ dfs.cpp, I'll execute it again, and I will just do ./a.exe. And let's just track the execution as well. So I just do ./a.exe. Let me open the graph, and where is our output? All right, so here we see that we start our journey at the node 0. So that is like processing node 0. Then we have processing node 1. So from 0 we jump to 1, and we are doing the processing of node 1. Then from 1 we jump to 2. So we do processing of node 2, and when we are at 2 we see that there are no more adjacent nodes to 2 that needs to be processed. So we simply say that there are no more adjacent unprocessed neighbors to 2. Okay, so all the neighbors to 2 are being processed. So we come back to 1. Okay, so 1, when we come back to 1 we see that are there any neighbors to be processed. So it simply says that there are no more adjacent unprocessed neighbors to 1, because 2 is done, 0 is also done. All right, so we come back to 0. And when we come back to 0, we see that 3 is not yet processed. So the control will not say that there are no more unprocessed neighbors to 0. It will say that processing node 3, because from 0 it will jump to 3. It will mark this as visited, and it will say that there are no more adjacent unprocessed neighbors to 3. Okay, so because there are no more adjacent neighbors to 3 that are not processed, because 3 has only one neighbor, and 0 that is already marked as visited. All right, so it will say that there are no more adjacent unprocessed neighbors to 3, and then there are no more adjacent unprocessed neighbors to 0, because 3 is done, 2 is done, 1 is done. So there are no more adjacent neighbors, and here we conclude the DFS program. Okay, so this was a very elaborate video that I did explaining you each and every step about this particular function over here. Okay, so in case you have any doubt, you can just write it in the comments. I hope you would have stayed till now for learning such a simple concept. But then if you have stayed till now, I hope that the concept related to DFS of a graph must be clear to you. All right, that's it for now. Cool. Bye bye.